Hi, my name is Caroline Porterfield, and this is my Physics 2212 Lab 6 report on Faraday's Law. Today we will go over an introduction, some models, the experiment itself, the code, discussion of the data, and some conclusions. The purpose of this lab is to investigate magnetic induction and the formation of currents by examining the motion of a bar magnet dropped through an aluminum tube and comparing the measured behavior to simulation results. A quick overview of results is that the experimental time was equal to 1.286 seconds and the computational time was calculated to be 1.17 seconds. The system was the bar magnet and the aluminum tube, and the surroundings was everything else. The analysis was done using a computational model called GlowScript, and the experimental model was a bar magnet following through an aluminum foil tube. We then compared observed versus predicted times. The fundamental physics principles for this lab are Faraday's law, Biot-Savart law, Newton's second and third law. For Faraday's law, this is when the magnetic field passing through a loop changes. It creates a voltage in that loop. The faster that the magnetic flux changes, the larger the induced voltage. This induced voltage always acts in a direction that tries to oppose the change that caused it. E is the induced voltage, N is the number of terms, and we have a magnetic flux, and T is time, change in time. Biot-Savart law is when any piece of wire carrying current creates a magnetic field around it. The size of this magnetic field depends on how strong the current is and how far away you are from the wire. The direction of the field follows the right-hand rule. Change in B is the magnetic field contribution. Mu naught is the permeability constant, I is current, change in L is the length element, R hat is the unit vector from wire to field point, and R is the distance from the segment. As for Newton's second law, it is the total net force acting on an object, and it determines how its momentum changes over time. More net force means a faster change in motion, and this is the change in momentum over the change in time. Newton's third law is whenever one object applies a force on another, the second object pushes back with equal size force in the opposite direction. The experimental setup began with dropping a bar magnet through an aluminum foil tube and measuring the time it took for the magnet to fall through the tube. Then we repeated this for a total of 5 times and calculated the average amount of time. The assumptions were that air resistance is negligible, the bar magnet acts as a magnetic dipole, and the only forces on this system are magnetic and gravitational forces. This is the experimental setup shown here. Now the experimental data. As you can see here are the dimensions of the tube and the magnet information. The average fall time is calculated to be about 1.286 seconds. Now the computational model initial conditions. The physical constants are shown here and the properties of the tube and the magnet. On the right shows the code for the magnetic field of the bar magnet and the change in magnetic flux that occurs. Now the results for the continued computational. Oh, here's the part of the code that calculates all the forces acting on the magnet, and you can see the magnetic force acting upwards and the gravitational force acting downwards. After adding these two together, we get the net force. We then updated the velocity and position of the bar magnet. Now for the results. The time in the tube for the computational model was 1.17876 seconds. The graph shows that as the magnet enters and leaves the tube, the gravitational force is greater than the magnetic force. This causes the magnet to accelerate. In the middle of the tube, the forces balance out, which you can see as at the constant velocity on the graph. This was right around the experimental model, but more precise due to the lack of human error. Now, interpreting the simulation. First, which color corresponds to the clockwise current viewed from above, and which for the counterclockwise? And how can you tell? Blue represents the clockwise current and red represents counterclockwise based on Lenz's law, and the direction of the system opposes the change in magnetic flux. What happens if you flip the magnet around? The magnet will still fall, but the induced current directions reverse. How does the real world total time in tube compare to the computational model, and why might the model be more accurate? The simulation time was longer than the real time. The model avoids human timing error and uses exact measurements, making it way more precise. What does the shape of the velocity versus time graph plot show, and about the forces on the magnet? Gravity dominates as the magnet enters and exits the tube, but inside the tube, the magnetic and gravitational forces balance, creating a steady velocity, which is what we saw on the last slide. Some potential errors were measurements because the stopwatch was started or stopped precisely, which could lead to an inaccurate dipole moment. They weren't stopped precisely. And also friction because the magnet hit the sides of the tubes on the way down, which slowed it down potentially. Now for the discussion. What if the resistivity of the conductor were reduced as close as possible to zero? How would the dynamics change of the falling magnet change? The decreasing resistance would increase the reduced current based on Ohm's law, which is V equals IR. This would produce a stronger opposing magnetic field, which would lead to the magnet slowing down more. And what if holes or slots were cut into the tube? How would this affect the ring currents in your model? In the tube, there would be less current rings, which would make a weaker opposing magnetic field, and then the magnet would fall faster. In conclusion, we learned in conclusion, we learned about the motion of a bar magnet after being dropped through an aluminum tube. Thank you for watching.